Hi everybody, I hope this video finds you well. In today's video, we're going to be starting into section 7.3 from your textbook, which introduces us to the next major technique of integration that we're going to be learning about, which is trigonometric substitution. To basically sort of summarize the video, what we're going to be doing here is we're going to take a look at this sort of motivating example here. Use this to sort of come up with an idea of how this trigonometric substitution is going to work and why we're going to use it, or in sort of what situations we're going to use it. Then we'll sort of talk about a little summary of this technique, and then we'll look at several more examples afterwards, sort of seeing how to actually use this technique and making sure that we understand how it applies in different situations. So, to start off with, we're going to try to perform this indefinite integral. So we want to try to do 1 over x squared times the square root of 1 minus x squared. So, the first thing that should pop out to you about this integral here is that we've got this radical in there with that 1 minus x squared in it. Now, of course, it would be nice if we could just take that like radical and apply it to the component separately, but we know that that's not how square roots work, right? A square root is an exponent, so it does not distribute over addition and subtraction. So we're sort of stuck with that term there, and that's going to be a pretty hassle-some term. Now, of course, we could say, well, there's a composition there, so maybe we should try something like u equals 1 minus x squared, and then the du would be like a negative 2x dx. The problem is that that would require like an x dx, and unfortunately, in our numerator, we only have a 1 dx. So it would be very challenging to actually find the du necessary to actually give this sort of a catalyst and actually be able to do that sort of u substitution. The other things that we've discussed so far, integration by parts, maybe. I suppose we could try to break this up. You know, quotients can be thought about as multiplications, but I'm not super excited about working with either part of this. And of course, it's definitely not a trigonometric integral, at least not yet. So let's talk about a sort of new technique. And this whole technique sort of focuses on trying to remove the issue posed by that square root of multiple terms, right? That square root of 2 terms inside that radical. So what we're going to try to do is we're going to try to come up with a substitution, specifically a trigonometric substitution, that when we plug into here, we can then get a Pythagorean identity, and that Pythagorean identity will allow us to change this from 2 terms into a single term. Once it's into a single term, we can actually apply and simplify that square root and then hopefully proceed from there. So if we think about it, this sort of might resemble, this 1 minus x squared sort of resembles like 1 minus sine squared. And we know that that is equal to cosine squared. So if we could replace that 1 minus x squared with 1 minus sine squared, then we would have cosine squared, and of course square root of cosine squared would just be a cosine. So that would make things tremendously more simple. So we're going to try this substitution. Instead of letting our new variable be a function of x, we're going to let x be a function of our new variable. So we're going to try to do x equals sine of theta. And again, this theta is just going to be a new variable, just like in u substitution, it's the variable u. Now we're going to use theta just to sort of help us separate this new technique. So we're going to let x be equal to a function, in this case, sine of our new variable. Now, of course, we know that when you substitute into an integral, you can't just substitute for the variable, you also have to substitute for the differential. So let's differentiate this. Dx would be equal to the derivative of sine, which is cosine theta, d theta. And we can just plug that in directly into there. So let's see what happens under this substitution. So we have our integral 1 over. This x squared here can become a sine squared. So we have 1 over sine squared theta. Then we have our square root. And then we have 1 minus sine squared theta. And then, instead of that dx there, we have this cosine theta. So we have cosine theta d theta. Now, there's some good and some bad here. The good is that this is a proper substitution in the sense that everything now is in terms of theta, and our differential is d theta. So it's not like where we have to do any more substituting. This is a perfectly fine form. The downside is it's pretty messy, right? It's got all these trigonometric functions in it, and it's still got that radical. But let's remember the point. The point was that this 1 minus sine squared, we chose sine to build this Pythagorean identity. So let's pop that cosine squared in there. We get the integral of 1 over sine squared theta, square root cosine squared theta. And then we still have our cosine theta d theta here. Now, that's a little bit better because now instead of having two terms inside that radical, we only have one term. But even better than that, now we can actually apply the square root to that square and cancel those out. So not only have we removed two terms, reduced two terms to one term, but we can now even get rid of that square root. So if we do that, we get 1 over sine squared theta, cosine theta, and then we have cosine theta d theta. Okay, now this is still pretty complicated. There's all these different trigonometric functions in there, but at least there's no more radical. Also, all these trigonometric functions are multiplied or divided, so we can cancel things. So notice that this cosine theta and this cosine theta can cancel. And we now have the integral of 1 over sine squared theta d theta. Now, we're not particularly thrilled by having a trigonometric function in the denominator, so why don't we rewrite this as a different trigonometric function? We can actually rewrite this as cosecant squared d theta. And it maybe takes a little remembering, but this is actually something we know how to integrate, right? This right here, except being off by a negative sign, is exactly the derivative of cotangent, right? We know that the derivative of tangent is secant squared, and the derivative of cotangent is negative cosecant squared. So this right here, we can integrate directly as negative cotangent theta plus c. And in terms of integration, we did it. We're done. We actually finished this integral, even though it was so messy to begin with. Now, the only challenge that's sort of left is that we need to unpack this substitution. Now, there's a really horrendous way to unpack it, which is not how we want to do it. One way we could unpack it is we could say, okay, if x is equal to sine theta, then theta is arc sine of x, right? We could try to use an inverse trig function, and then we could call this negative cotangent of arc sine of x. But that's a really messy expression, and we can actually do a lot better. The trick to sort of doing better is to draw a diagram to sort of help us unpack this substitution. So let's recall that our substitution was that sine of theta was equal to x. So let's draw a little diagram here. Let's draw a right triangle. So we're going to make this a right triangle, and I'm going to just label any one of the angles as theta. Now, let's label this triangle so that sine of theta is equal to x. Now, you can remember that sine is your opposite over hypotenuse, and of course this x, we can sort of think about it as x over 1. We can think about it as that ratio. I mean, we could think about a lot of other ratios. We could think about it as 7x divided by 7 or x squared divided by x, but let's take the easiest one, just x divided by 1 there. Okay, so if sine is your opposite over your hypotenuse, then that must mean that we can have our opposite be x and our hypotenuse be 1. Well, as you guys know, there's a Pythagorean theorem that allows you that if you know two sides of a right triangle, you can figure out the other one. So this missing side here, I guess which we would call the adjacent, so a, we know that a squared plus x squared is supposed to be 1 squared. That's the Pythagorean theorem. And that would tell us that a is supposed to be the square root of 1 minus x squared. So we actually know that this a here is supposed to be the square root of 1 minus x squared. Okay, so why does this triangle help us? Well, what did we want in our answer? We wanted cotangent of theta. What is cotangent? Well, tangent is your opposite over your adjacent. So cotangent is your adjacent over your opposite. Well, we know our adjacent is the square root 1 minus x squared, and we know our opposite is x. So we can actually take this thing here and rewrite it. So we're going to take this here and rewrite it back in terms of x as negative. And again, we say cotangent is your adjacent, which is square root 1 minus x squared, over your opposite, which is x, plus c. And notice that there's a nice, much cleaner expression than negative cotangent of arc sine of x. That's really ugly. This is a much cleaner expression, and it is the antiderivative of our function there. Okay, so before we jump to summarizing this, let's sort of recap what we did here. The main idea was that we recognized that this radical was going to prove to be difficult because that radical cannot be sort of broken up into other pieces. So what we tried to do is we tried to pick out a trigonometric function that upon substitution in there would create a Pythagorean identity. Then once we plugged that in, we made sure to also substitute for dx. We followed through. We used the Pythagorean identity to convert the two terms in here to a single term. Then we were able to actually apply the square root, and then from there, it was just simplification. At the end, we had a little bit of sort of messy trigonometry to just sort of undo the substitution, but that really is just part of a sort of undoing of the substitution. It's not really part of the integration there. So what I really want you guys to focus is on this idea of sort of trying to remove a radical by choosing an appropriate trigonometric function. So what would happen if this looked slightly different? Well, we could use a different trigonometric function. So let's go ahead and give ourselves a quick summary of this method by sort of reminding ourselves about the different Pythagorean identities that we've talked about, or that you guys have talked about in your trigonometry classes. So our main idea here is that to simplify radicals inside of an integrand, we can attempt to use the following Pythagorean identities. 1 minus sine squared is cosine squared. We also know that 1 plus tangent squared is secant squared, and we know that secant squared minus 1 is equal to tangent squared. So what that means is that inside of a radical, so inside of a square root, we see an expression of the form a squared minus x squared, which is what we saw over here with the a being equal to 1. Then what you guys can do is you can attempt to use the trigonometric substitution x equals a sine theta. Why will x equals a sine theta work well? Well, if you do that, if you do x equals a sine theta, then your a squared minus x squared will become a squared minus, and if we plug in a sine theta into x squared, we'll get a squared sine squared theta. And then if you take that, you can factor that out as a squared. Let's zoom in a little bit to make that a little easier to write. And if you factor out that a squared, I don't like those arrows, right? This one we want an equal sign. A squared 1 minus sine squared theta. And then you'll be able to replace that 1 minus sine squared with a cosine squared. If you see something of the form a squared plus x squared, then you can attempt the trigonometric substitution x equals a tangent. And you can see why that'll work. A squared plus x squared will become a squared plus a squared tangent squared. And then you factor out your a squared, and you get 1 plus tangent squared theta. And then, of course, what you can do is you can replace that tangent squared with a secant squared. So again, all of this is trying to reduce those two terms into a single term. Finally, if you see something like x squared minus a squared, well, if you see something like x squared minus a squared, you can try a equals secant theta. So you would get you'd get a squared secant squared theta minus a squared. Do the same trick, factor out the a squared, and you get secant squared minus 1. And then, of course, Pythagorean identity lets you change that into a tangent squared. So this basically tells you that depending on what you would see inside of your radical, you can choose an appropriate trigonometric substitution. In our first example, we didn't have to worry about that a, that constant. We just had a 1 there, which is why we use sine of theta. But I just wanted you guys to see more generally that if you have a constant, it doesn't matter if it's 1 or some other number, you can still use this trigonometric substitution approach. Okay, so for the remainder of this video, we're just going to go through some more examples of sort of identifying this, using the appropriate substitution, and just getting more comfortable with how this technique really works. But as we do this, just keep in mind, this technique is really basically used for seeing these types of expressions inside of a square root. That's where you want to use this trigonometric substitution approach. Okay, let's go ahead and take a look at our next example. So we're going to try to perform this indefinite integral. We have the integral 1 over 4 plus x squared to the 3/2 dx. First thing we should recognize is that that 3/2 is very similar to a square root, right? That is 4 plus x squared to the 3/2 is really the same as square root 4 plus x squared all cubed. So that's a radical, and that's why we're going to use this trigonometric substitution approach. What should we try to do here? Well, we're going to recognize that the 4 plus x squared is the same as 2 squared plus x squared. That's how we can think about it as a sum of two squares. So if we look back, something squared plus x squared, that means we should try to use a tangent theta. So our substitution in this case is we're going to try x equals 2 tangent theta. So our substitution is going to be 2 and then tangent theta because it's a squared plus x squared. Whenever you're doing this, you got to make sure you also substitute for the differential. So we get dx is going to be 2. Derivative of tangent is secant squared theta d theta. Always got to do this. Just like with u substitution, you always have to take care of not only the variable substitution, but the differential substitution. Okay, let's go ahead and plug this in and see what happens here. So we have the integral 1 over 4 plus, we chose to put in 2 tangent theta, so squaring that is going to give us 4 tangent squared theta, all to the 3 halves. And then our dx is now being replaced with that 2 secant squared. So we have 2 secant squared theta d theta. Okay, first thing we need to do is remember the whole point of this is to get some sort of Pythagorean identity. So we need to factor this 4 out, and notice that the choice of 2, because we squared it, means that each term has a 4, so we can factor that 4 out. So let's go ahead and do that. We get the integral 1 over 4 is going to be factored out, but it's still going to be to the 3 halves. So we have 4 to the 3 halves. And then we have 1 plus tangent squared theta, all to the 3 halves. And then we still have our 2 secant squared theta d theta on the outside. Okay, so we can do a couple simplifications here. 4 to the 3 halves, that's the square root of 4, which is 2, and then raised to the 3rd power. So that's going to be an 8. So we have the integral 1 over 8. In here, 1 plus tangent squared, well, that's a Pythagorean identity. That's going to be secant squared. So we're going to end up with secant squared theta. And of course, we still have our to the 3 halves there. And then 2 secant squared theta d theta. Okay, let's do a little bit of simplification. Let's cancel the 2 over 8 and make it a 1/4. And I'll just stick the 1/4 outside. And let's also go ahead and apply secant squared to the 3 halves. Power to a power you multiply. 2 times 3 halves is going to cancel, and we're just going to get a cubed. So we should get 1/4 times the integral. That's the 2 divided by 8. That's giving us our 1/4. And then we said that this is going to become 1 over secant cubed. And again, that's power to a power when we're multiplying those exponents. And then we still have our secant squared out here. Okay, things are getting simpler at each step. Now we have another simplification. We can cancel here. And we can get 1/4 integral 1 over secant theta d theta. Okay, we're not thrilled about that being in the denominator, but actually this is even easier. The integral, what is 1 over secant theta? Well, secant is 1 over cosine, so 1 over cosine. That means this is actually just cosine. So we have the integral cosine theta d theta. We know how to integrate cosine theta. This is just going to become 1/4 sine theta plus c. So we went ahead and we finished our integration. Now everything we have to do after here is just going to be undoing our substitution. So let's go ahead and we'll sort of unpack this over here. We'll sort of come all the way back up. We'll zoom out a little bit so we can make this a little bit easier here. So let's just rewrite what we had. We have 1/4 sine theta plus c. So that's our actual antiderivative. Now we just got to get back in the variable we started with. So initially we had x equals 2 tangent theta. I always like to just sort of reverse the order I write it in. When I'm doing the substitution, I like to read it left to right. X equals 2 tangent theta. When I'm undoing it, I'm going to sort of think about it as 2 tangent theta is equal to x. Let's get that tangent isolated since we're trying to reverse the substitution. Tangent theta is x over 2. So let's draw ourselves a triangle. There's theta. There's our right angle. Once again, I'm going to think about this as equal to x divided by 2. Right? So I can think about tangent as your opposite over your adjacent. So let's label those. That means we can put the x here and we can put the 2 here. So that tangent of this angle is automatically x over 2. Well, then we can use Pythagorean theorem to determine the hypotenuse. The hypotenuse squared is supposed to be x squared plus 2 squared. which means that the hypotenuse is supposed to be the square root of x squared plus 4. Okay, so we have that our hypotenuse is x squared plus 4. What did we want? We wanted sine of theta, which of course is your opposite over that hypotenuse. So our 1/4 sine theta plus c can be replaced as 1/4. Opposite is x, so x divided by the hypotenuse, which is square root x squared plus 4, and then plus c. So there we go. There's our antiderivative. So this one, a little bit different because we used tangent because we had a plus between these two. So we wanted to choose a different trigonometric function to get a different Pythagorean identity. And we had to be a little bit careful because this time it wasn't a 1. So we had to do 2 times our trigonometric function to make sure we could factor that 4 out. Otherwise, very, very similar. Okay, we've got a couple more examples to do, but one thing I just want to note here is that you should not be surprised that in both of these examples, the missing side that we had to determine is always directly connected to what caused us to do the substitution. Let's see what I mean by that by just going back and taking a quick look. If you look at this one, we sort of talked about how that square root of 1 minus x squared is what sort of motivated us to try this trigonometric substitution. You will notice that the missing side, which happened to be the adjacent in this case, was directly equivalent to square root 1 minus x squared. And in this case, the thing that sort of motivated us to do this substitution was 4 plus x squared, and it is not a shock that the missing side, which in this case was the hypotenuse, was square root x squared plus 4. That's really because we're choosing these trigonometric functions based on the Pythagorean identity that's going to help us remove those two terms. So you should usually expect to see that sort of missing side that you have to solve for in the triangle when you're undoing the substitution to exactly match what caused you to do the substitution in the first place. Okay, let's go ahead and take a look at another example. So we're going to try to perform this indefinite integral, the integral of square root x squared minus 1 over x cubed. So this guy here, right, we can immediately see the x squared minus 1 inside the radical is what's going to sort of motivate us to do that. In this case, we can think about x squared minus 1 as being x squared minus 1 squared. So we don't want to use tangent and we don't want to use sine. Instead, if we go back, we have something of this format. We want to try to use secant. You might say to yourself, well, can't we just rewrite this as like negative 1 minus x squared and use a negative sign and then use the sine function? Well, you got to be very careful about like factoring out negatives when you're inside a square root. So that's really, really not a good idea here because of the fact that we have that square root function. So when you see something where it's x squared minus a constant, you definitely want to make use of the secant substitution. So in this case, we're going to do x is equal to secant theta. And then we have to do our differential, which will be secant theta tan theta d theta, because that's the derivative of secant. Let's go ahead and plug this stuff in. So up top, we're going to have secant squared theta minus 1. Down below, we're going to have secant cubed because we're plugging in x equals secant theta. And instead of that dx, we're going to have secant theta tan theta d theta. Okay. Now, you can immediately start canceling if you want, but I always like to focus on why we're doing the substitution, which is that to get that Pythagorean identity and to simplify the radical. So let's focus there before doing anything else. Secant squared minus 1 is tangent squared, so we get the integral square root tangent squared, which again is why we're sort of choosing to do this. And we've got our secant tangent d theta. Okay. Here now we can apply the square root and simplify that. So we have the integral tan theta over secant cubed theta, secant theta tan theta d theta. Okay, we can simplify a little bit more now. We can start combining and canceling. So let's cancel that and then multiply these two together. So it looks like in our numerator, we have tangent squared, and in our denominator, we have secant squared d theta. Now, in section 7.2, we spent a long time talking about things like products of sines and cosines, products of tangents and secants, and how to work with them. We didn't talk a lot about quotients, and that's because for quotients, we want to always just be able to sort of rewrite this. So notice that this secant squared can be brought up as a cosine squared. So we can think about this as a tangent squared cosine squared d theta. And then, if we remember that tangent is actually sine squared over cosine squared, we can cancel those cosines and just be left with sine squared. So after all that, we can reduce this to a sine squared d theta. Now we can remember back and say, okay, what did we say in 7.2 about integrating powers of sines and cosines? Well, we said fingers crossed that we get an odd exponent so we can save one, convert the rest, and use u substitution. Unfortunately, this time we have a sine squared, an even exponent. So this is where we're going to need to use our double angle identity. So we're going to rewrite this again as 1/2 minus 1/2 cosine 2 theta. That's the double angle identity for sine squared. Now we can go ahead and integrate this, and we should get 1/2 theta. Here, we integrate the cosine, and we get a sine, but since this is a linear substitution, we do get a factor of 1/2 outside. So we should get minus 1/4 sine 2 theta plus c. Now, if you're a little uncomfortable jumping from here to here, just keep in mind that that's a u substitution. You could always write out the u sub, u equals 2 theta, and go from there. But since we're going to be seeing a lot of these linear substitutions, I'm hoping that pretty soon you guys can just make that jump from there to there. Okay, now we have a lot of sort of unpacking to sort of do from this. So we finished the antiderivative, so that part's done. Now it's just about sort of algebraically manipulating it back into our original variable. So let's grab this and sort of bring this all the way back up to where we actually wrote out our substitution. So we have 1/2 theta minus 1/4 sine 2 theta plus c. Okay. Now, even if we start to use our standard trick of drawing out the triangle, that triangle is going to be based on theta. It's not going to be based on 2 theta. So at this point, the first thing that we want to do if you ever have a different argument than you originally started with is you're going to need to put this back in terms of the original argument, which means the original theta. So now we're going to use the double angle identity the opposite way to rewrite this in terms of theta. So we can rewrite this 1/2 theta minus 1/4 times 2 sine theta cosine theta plus c. Then we simplify 1/2 theta minus 1/2 sine theta cosine theta plus c. Okay, now this should be a little bit easier to unpack. So let's remind ourselves what our substitution was. It was secant theta was equal to x. Again, I like to just rewrite it the opposite way now. I mean, it doesn't change anything, but just reading left to right now helps us sort of remind ourselves we're undoing the substitution. Okay, I'm going to again think about that as being x over 1 here. So I'm going to draw ourselves a right triangle, label an angle as theta. Okay, secant is going to be your hypotenuse over your adjacent. So we can label the hypotenuse as x and the adjacent as 1. And then we can go ahead and figure out the unknown opposite here. So the opposite, so we know that 1 squared plus the opposite squared. I don't like that. I mean, this is bad notation. Let's put OP. All right, for opposite equals x squared. So that tells us that the opposite squared is actually, we can just jump all the way there, square root x squared minus 1. And again, unsurprising that the missing side is what caused us to do this trigonometric substitution in the first place. Okay, so now we can start to unpack this. First thing we need to unpack is theta itself. Unfortunately, if you're forced to just unpack the angle by itself, there is nothing clever you can do with the triangle. You're just going to have to invert this using an inverse trigonometric function. So if secant theta is equal to x, then we can just say theta is arc secant of x. So if you're ever left with just a single theta, you're going to have to use an arc in an inverse trig function. It's not the worst thing. It's just we try to avoid it in these situations. So we get 1/2 arc secant of x. Okay, that's the best we can do there. Minus 1/2 sine of theta. Well, that's the opposite over 1, which is that square root x squared minus 1. And then cosine theta, which is the adjacent. Oh, I'm sorry, that sine of theta is incorrect. That's the opposite over the hypotenuse. Oh. So that should be square root x squared minus 1 divided by x. Sorry about that. Sine, of course, is opposite over the hypotenuse. And then the cosine is your adjacent over your hypotenuse, which is 1 over x plus c. And there we go. There's our expression for our antiderivative. Could we clean it up a little bit? Yeah, I guess we could just call that an x squared there. So I guess the best phrasing of this would be 1/2 arcsecant of x minus 1/2 square root x squared minus 1 over x squared plus c. That's pretty decent phrasing of it. Okay, so a little bit messier here because we had to make use of a double angle identity. Just keep in mind that if you use a double angle identity one way, you're going to also have to undo the double angle identity later so that you can actually undo the substitutions. Let's see how trigonometric substitution works with a definite integral. So far, everything we've done is indefinite. So let's take a look at doing a definite integral. So we're going to try to evaluate this one as we're going to try to do it as a definite integral here. So we have the integral from 1/6 to the square root of 2 over 6 of square root 1 minus 9x squared over x dx. Okay, so there's going to be some manipulations at the beginning here. Notice that we want the x squared by itself. If we go back to our sort of summary, we always talked about the x squared sort of being a term by itself. So we're going to need to do a little factoring at the beginning here. So let's start by factoring out a 9 out of this. So if we do that, we should have the integral from 1/6 to root 2 over 6. If I factor out a sort of 9, I'll sort of do it in two pieces. You can think about this as 9 times 1/9 minus x squared over x dx. Right, so I can factor that 9 out even though the 1 doesn't have a factor of 9 by making it 1/9. That gives us our x squared. And then, of course, we can bring that 9 out of the radical as a 3. So we get the integral from 1/6 to root 2 over 6, 3 times the square root of 1/9 minus x squared over x dx. Okay, now it's in our format there. We see a number minus x squared. We can go back and check what our options were. For a number minus x squared, we said we should use a equals sine theta. So as long as we know what our a is, we know that we're going to be using sine here. So we can think about 1/9 minus x squared as 1/3 squared minus x squared. So that means the substitution we're going to attempt to do is 1/3 sine theta. All right, that means the dx should be 1/3 cosine theta d theta. So we've got our x and our dx. Now, got to remember though, this is a definite integral. So we have the option here of changing our bounds. Now, if we decide to change our bounds, the great thing about that is that means we don't have to undo our substitution. We can just go with the new bounds, and we can avoid that whole step with the triangle. So let's go ahead and change our bounds. The original x bounds were root 2 over 6 and 1/6. So we can try to think of the theta bounds. How would we do that? Well, we'd have to solve this. So square root of 2 over 6 is supposed to be 1/3 sine theta. If you actually start to solve that, well, you can multiply the 3 over, and you can get root 2 over 2 is sine theta. And, well, when is sine of theta equal to root 2 over 2? We know that that means theta is actually pi over 4. Same thing here. We can say 1/6 is 1/3 sine theta. Again, just plugging in that we know what x is in this, so I'm just trying to change our bounds. Multiply by that 3, we get 1/2 equals sine theta. And that tells us that theta is pi over 6. Right? Because we know that when is sine equal to 1/2, it's at pi over 6. Okay, so we can change our bounds and do this substitution. So let's do all that. We now have the integral. Instead of from 1/6 to root 2 over 6, we're now just running that integral from pi over 6 up to pi over 4. We still have our 3 right here. Inside of this, we now have the square root 1/9 minus, plugging in x equals 1/3 sine theta, squaring that, we get 1/9 sine squared theta. Notice that that means we're going to be able to factor out that 1/9. Then dividing by our x, we have 1/3 sine theta, because that's what we plugged in for x. And then we got to make sure we plug in our dx, and we get a 1/3 cosine theta d theta. Okay? little bit of a mess right now because of all the fractions and everything, but let's try to simplify it as much as possible. Notice that the 1/3 here and the 1/3 here can cancel, so we can forget about those. And for now, we can go ahead and factor out this 1/9. When it comes out of the square root, it's going to come out as the square root of 1/9 is 1/3, and it's going to cancel with that. So we can reduce this to pi over 6 to pi over 4, square root 1 minus sine squared theta over sine theta, cosine theta, d theta. So in this case, all of those sort of fractions and stuff canceled out. All right, now let's not lose track of why we did this. This 1 minus sine squared is a Pythagorean identity, so we can simplify there. Integral pi over 6 to pi over 4. This should be square root cosine squared theta over sine theta, cosine theta d theta. Okay. Whole point of using that Pythagorean identity is now that that's a square, we can apply the square root. So we get the integral from pi over 6 to pi over 4, cosine theta over sine theta times cosine theta d theta. Okay, so at this point, we got to sort of try to figure out how we're going to approach this integral. So we need to try to come up with a sort of clever way to examine this guy here. Well, I guess we could try to rewrite it. We're not going to be particularly thrilled about rewriting it, because if we start to rewrite this, I guess we could rewrite it as cotangent times cosine. But cotangent times cosine is not particularly great for us because we didn't talk about products of cotangents and cosines. So we could maybe try to multiply these together and take a look at what we get from there. So let's go ahead and bring this all the way up here. So let's just multiply it out and try to view it like that. So integral pi over 6 to pi over 4. Looks like we have cosine squared theta over sine theta d theta. All right, again, not great to rewrite it. We could try a u sub, right? We could try to do u equals cosine theta, but the du is in the wrong spot. It needs to be in the numerator, not in the denominator. Well, if nothing else sort of works well, we could always try a Pythagorean identity, just put everything in terms of sine. So we could say pi over 6 to pi over 4, 1 minus sine squared over sine d theta. And, well, that looks a little bit better. I can now divide the sine into both, and we get the integral from pi over 6 to pi over 4. 1 divided by sine is cosecant theta, and sine squared divided by sine is just minus sine theta. Okay, this is looking much better. We know how to integrate cosecant. It's very similar to how we integrated secant. Remember, secant is ln secant plus tangent, so cosecant should be negative ln cosecant plus cotangent. And then we definitely know how to integrate sine, so we can go ahead and do that. So we get negative ln absolute value cosecant theta plus cotangent theta. That's our integral of cosecant. If you haven't seen that integral before, that's exactly the parallel for secant theta, and you can sort of confirm that, or you can also just add this to the table of integrals that you know. And the integral of negative sine is going to be positive cosine theta. And then we evaluate that from pi over 6 to pi over 4. And at that point, we should be able to just plug everything in and evaluate it. So negative ln, let's plug in pi over 4. Cosecant at pi over 4, well, sine at pi over 4 is root 2 over 2. Cosecant is going to be 2 over root 2, so that just sounds like root 2. Cotangent at pi over 4 is going to be 1, so we get that. Plus cosine of pi over 4, which sounds like root 2 over 2. And then we can subtract, and we can evaluate at pi over 6. So we would get negative ln absolute value. Cosecant at pi over 6, well, sine at pi over 6 is 1/2, so cosecant is going to be 2. And then cotangent at pi over 6, well, I guess that cotangent is what? Cosine over sine, so that's going to be root 3 over 2 over 1/2, so it sounds like root 3, so plus root 3. And then cosine at pi over 6 is root 3 over 2. So plus root 3 over 2. So I'm not going to go any further than that. We'll just leave it there. But there is our definite integral. Now, this guy was a little bit messy because of the, plugging in the bounds is always making it sort of arithmetically messy. But do keep in mind that we got to avoid undoing the substitution because it was a definite integral and because we decided to change our bounds. So in these cases, I would always recommend changing your bounds so that you can avoid having to undo the substitution at the end. All right, let's get to our very last example, which is going to be very similar to the ones that we sort of done here, but just with one little added twist. You're not going to see this very frequently, but I'd like to at least show you guys one example of it. So we're going to try to perform this indefinite integral, the square root of x squared plus 8x plus 17 dx. Now, at the beginning here, we should immediately recognize that this doesn't look anything like the other ones that we've done, except for the fact that we have a square root in there. In other words, this in here doesn't look like the previous ones because it's got that 8x. It's not just written as an x squared plus a number or x squared minus a number or something like that. So what we're going to attempt to do here is we're going to try to complete the square so that we can rewrite this as something squared plus a number. So let's go ahead and try that. We can rewrite this 8x squared plus 17 as... How do we complete the square? Well, divide this by 2. So it would be x plus 4 and then squared. And then if you want, off to the side, you can actually square that. That would give you ax squared plus 8x plus 16. So since we have plus 17, it must be equivalent to x plus 4 squared plus 1. So in other words, we can view this as this here. So this is, again, not like something you're going to encounter too much, but in case you ever see a radical with a quadratic inside, well, you can always complete the square to rewrite that quadratic as a square plus or minus a value. All right, so now that we have that, we can view this as the integral x plus 4 squared plus 1 dx. Now, let's do a substitution, not a trigonometric substitution yet, but let's do a u substitution so that we don't have to view this so weirdly. Let's go ahead and do u equals x plus 4. That means that du is going to be dx. And now we can view this as the square root u squared plus 1 du. Now this is in a format that we're very comfortable with. If we go back to our summary, we have something squared plus 1. So we would use this. We want to use our tangent substitution. So let's go ahead and do that. So we're going to let u equal tangent theta, which means du is going to be secant squared theta d theta. So let's go ahead and plug that stuff in. We're going to get square root tangent squared theta plus 1 times that secant squared theta d theta. Whole point of doing that is that builds our Pythagorean identity there. So this is square root secant squared theta and then secant squared theta d theta. Okay, now that we've used the Pythagorean identity, we should be able to simplify that square root. So this is secant theta, secant squared theta d theta. Multiply that out, and we get the integral of secant cubed theta d theta. Now, seeing that secant cubed, we're not thrilled about that. We like even powers of secant, but secant cubed was an integral that we took the time to actually go through and do sort of just as a single example. And we said that it's an important one to have down as with sort of just knowing that antiderivative form. So we know that this becomes 1/2 secant theta tan theta minus 1/2 ln secant, plus 1/2 secant theta plus tan theta plus c. So that was our integral for secant cubed that we established in the sort of last video when we went through and we actually did this as an integration by parts. Remember, we sort of broke it down as a secant theta and a secant squared theta, and then we sort of went and worked from there, and we got this expression here. So now that we have that, we can start to undo this substitution. We can start by trying to undo this. So we can say tangent theta is equal to u. Draw ourselves our triangle, label an angle as theta, make it a right triangle. Think about this as u divided by 1. Tangent is your opposite over your hypotenuse, or sorry, over your adjacent, excuse me. Then we can determine the unknown hypotenuse there. Hypotenuse squared is going to be u squared plus 1 squared. So that tells us that our hypotenuse is the square root of u squared plus 1. So we can go ahead and plug in the stuff that we need. Our tangent is just going to be equal to u, so wherever we see a tangent, we can place a u. And our secant, well, secant is going to be your hypotenuse over your adjacent, so it's just going to be that square root u squared plus 1. So let's go ahead and sort of bring this up to here. So what we're going to have then is, we can zoom out a little bit so we can sort of see the stuff together. We can have 1/2, that's secant, like we said, is going to be the hypotenuse over the adjacent. So it's going to be that square root, u squared plus 1. The tangent is just u, so u. Plus, I'll have to probably write this on the next line, 1/2 ln. The secant, we said, is square root, u squared plus 1, plus the tangent, which is u, and then plus c. Okay, we're almost done undoing the substitution. Now we just got to pop back in that x plus 4. So it looks like we get 1/2 times the square root x plus 4 squared plus 1 times x plus 4 plus 1/2 ln, absolute value, square root x plus 4 squared plus 1 plus x plus 4 plus c. This is very messy because of the fact that we had to sort of complete the square, so everywhere has all these x plus 4s in there, but this really is our antiderivative for that expression there. You guys are not going to see too many where you need to do this completing the square trick, but do be aware that if you ever see something that you suspect is a trigonometric substitution, but it is not in that form of x squared plus a number, x squared minus a number, or a number minus x squared, if you just see a quadratic in general inside of the radical, you can do this completing the square method, rewrite it as a square plus or minus a number, and then do your standard trigonometric substitution. All right, that wraps up section 7.3, trigonometric substitution. We've got one sort of last section introducing one more sort of technique of integration, which is section 7.4. We're going to talk about partial fractions, which is a great technique for any sort of rational function.